Okay. So to start, in the last class, I had sort of given out I'd suggested a little assignment. And I'm going to start today's class by working out parts of that assignment because we'll need it for what we need, what we're going to do ahead. Okay. So the assignment, if you remember, was to work out the operator form of the supersymmetry algebra in this 4 supercharge case, and then use it to find wave functions and so on. The wave functions and so on we won't talk about this class because we don't need it for going ahead. But the operator form of the supersymmetry we need, so we will discuss. So this could, you could think of this as when we first did the 2 supercharged quantum mechanics, I'd also suggested an assignment, which was the same one, to use what we have from the superspace, and to figure out the action of the supersymmetry operator in Hilbert space. Okay, so as a warm-up for working out the more complicated case, we'll first quickly review that case. Okay. So we're going back to like the first lecture. You remember we had Q1 was equal to half. Let me get my spectacles. So we had Q1 was equal to half sigma 1p plus sigma 2w. Q2 was equal to half sigma 2p minus sigma 1w. Okay, and you remember that we found it useful to eventually take complex linear combinations of these guys. So we defined q, which was equal to q1 plus iq2, which was sigma plus p minus iw, and we also defined q bar, which was q1 minus iq2, which was sigma minus of p plus iw. Okay, this was we already had in that case the operator form of the supersymmetry algebra. Okay, and now what we're going to do is to take this answer, which we already know, and compare it with what we get from the superfield formalism. Okay, so from the superfield formalism we had, Mummy, I'm teaching a class, I'll call you later. Okay. Okay, excellent. So we had, and please correct me if I'm getting this wrong. Okay, you remember that in our we had these psi and what we later called psi bar. Maybe when we were doing it we called it chi, and this was sigma minus and this was sigma plus. And we had worked out the supersymmetry transformation rules for each of these guys. So we'd worked out delta q on let's say x was equal to, now I'm writing it down sort of like from memory, and if I'm getting this wrong, please help me out. Minus I sigma psi bar, delta q on psi bar was 0, delta q on psi was equal to x dot minus iw. If somebody has their notes handy and can check this, that would be very nice. Okay. This is what I, just roughly reproducing it, this is what I got. The delta q bar of psi bar was equal to x dot plus I w, delta q of psi was equal to 0, and delta q sorry, delta q bar of x of x was equal to minus I psi. Which one?
The first one.
This was plus I psi bar, and this one is also plus. Okay. Okay, excellent. Okay. So now we've got these two different relations. We've got this, the superfield expansion. We've got the operator formalism, and we want to see how they match together. Okay? So the question that we're going to ask is, what operator relations allow us to generate these transformations? Okay. So let's see. The claim, what we want to do is to take delta q of anything of A is equal to A commutator q if A is bosonic. Oh, I hope my signs have. Okay, we'll change this around. Okay, and is equal to A anti-commutator q. We may have to change some orders around as we move along. If A is fermionic. Okay, notice that there are two choices you could have had. You could have put q at the beginning or q at the end. Okay, putting q at the beginning for the anti-commutator changes nothing, because A anti-commutator B is same as B anti-commutator A. But putting q at the beginning or the end for the commutator flips by a sign. Okay, now let's try this out and see if it's working. Okay, so iota times maybe. Let's start working components out. We'll see. Yeah, maybe there's an I. Okay, so let's see. So let's start with, let's just take the operator expressions and start computing these anti-commutators, commutators and anti-commutators. Okay, so let's start with trying to reproduce that. So suppose I take x commutator q. Okay, now q was, where were we? Sigma plus p plus I minus. Yes, so then we will get, because q has a p and p has an ix, so that's I sigma plus, right? Because we're using the fact that x commutator p is I. Okay, good. So I sigma plus, and that matches that guy up there. Okay, so now without an I. Okay, now let's look at, now we want psi bar anti-commutator q. Okay, we want psi bar anti-commutator q, but q was with a psi bar, so we just get 0. That matches that. And then we want psi anti-commutator q. Okay, but psi is simply sigma minus. Sigma minus anti-commutator sigma plus is equal to 1, so we get p minus I w. And that matches the x dot minus I w, because p was x dot, because our Lagrangian was x dot squared by 2. So the canonical quantization gives us p is x dot. Please. X and phi are the same. Sorry, where is phi? Chi. Yes, where is chi here?
Nowhere.
Nowhere.
But in the previous calculation,
Yeah.
x, that is x.
Oh, that's x. Sorry for the. That's how I write x. I'm sorry. Yeah, there's no chi. In the first few lectures, we used chi for what we now call psi bar. Okay, excellent. And just to complete this, let's also do the Q bars, just to be totally sure. So let's see. So if we hit Q bar with, so now what we want to do is to compute X commutator and commutator Q bar. That gives us the same thing, right? Because it's the same X commutator P is 1, so we get is I, so we get I sigma minus, okay, which matches this, because you guys corrected my signs. Okay, then there was X commutator, sorry, psi commutator Q bar. But psi was same as sigma minus, and Q bar comes with a sigma minus, so that's 0, which matches that. And then we get anti-commutator. Anti-commutator of psi bar with Q bar, which is equal to P plus IW, which matches X dot plus IW. Okay? So we see the rule. The rule is that we take the operator expression that we take the operator expression that we get from operator quantization and take commutators, anti-commutators, but put the guy on the right. Okay? Fine. So now we're going to do the same thing for the 4 supercharge case. We're going to do the same thing for the 4 supercharge case. We're going to take the transformation laws that we worked out last time in gory detail and convert them into operator expressions. Okay? Excellent. So now I'm writing down these transformation laws we worked out last time. Again, if I make a mistake, please correct me. Okay? So I'll just remind you about the model we were studying. We were now studying this 4 supercharge theory. The action for this theory was equal to phi bar dot phi dot minus I psi 1 dot psi 1 bar minus I psi 2 dot psi 2 bar minus W prime mod phi squared plus W double prime psi 1 psi 2 plus complex conjugate, which is the same thing as plus W bar double prime psi 2 bar psi 1 bar. Okay, this was the model we were studying. We will sometimes write down supersymmetry transformation rules involving F, the auxiliary superfield which we integrated out. And I remind you that F was equal to minus I W prime of phi, and F bar was equal to I W bar prime of phi bar. F is, thank you.
And double.
Then I messed this up. Yeah, W bar. F is plus I. Thank you. Okay. Something else that I will also remind you of is that the equation of motion of psi 2 that follows from this Lagrangian. The equation of motion of psi 2, so let's work this out. If we want the equation of motion for psi 2, we integrate by parts, take the dot there. So we get from here we get an I psi 2 bar. And here we get a minus switch. So we get minus W double prime psi 1 is equal to 0. Psi 2 bar dot. Thank you. Okay. And with all these, with all this in place, we worked out the commutation relations, which I'm writing down, but you will correct me. We've got delta Q1 on phi was equal to I square root 2 psi 1. Delta Q1 on psi 1 was equal to 0. Delta Q1 on psi 2 was equal to square root 2f, where f was all that there, right? F is I w prime bar, and f bar was minus I w prime. And delta q1 on f was equal to 0. Okay? Then we also had delta q2. Now, the rule for delta q2, if you remember, was you just replace 1 with 2, but also replace f with minus f. Because your superfield expansion had a theta 1, theta 2 f, which is minus of theta 2, theta 1 f. Okay? So we can just write this down now. So this was phi was equal to I square root 2 psi 2, delta q2 psi 2 was equal to 0, delta q2 psi 1 was equal to minus square root 2f, and delta q2f was equal to 0. Right? Then we had sort of independent data, which was how q bar acted on the phis, and we had delta q1 bar phi was equal to 0, delta q1 bar psi 1 was equal to square root 2 phi dot, delta q1 bar psi 2 was equal to 0, and delta q1 bar f was equal to square root 2 I psi 2 dot. Okay? And then once again we use the rule for 1 and 2 flip. So we get delta q2 bar phi was equal to 0, delta q2 bar psi 2 was equal to square root 2 phi dot, delta q2 bar psi 1 was equal to 0, and delta q2 bar f was equal to minus square root 2 I psi 1 dot. Okay? And then we had the second rule, which you remember from last time, which was that we could replace every q with a q bar and field with a bar, and no further signs, no signs with i's. You remember that. So now with these this table and that rule, we've got all supersymmetry transformation properties. So I'm not writing that down. Okay? So now we're going to ask the question, what are the supersymmetry operators? What are the supersymmetry operators in Hamiltonian language that generate these supersymmetry transformations? Okay, so let's remind ourselves what are Hilbert spaces. Okay, our Hilbert space is made out of the operators. It can be generated from the operators phi bar, and pi phi bar. This is in the bosonic sector, clearly, because we've got two bosonic variables. We're working with these complex variables, so the momentum conjugate to phi is phi bar dot. Right, so this pi phi is the same thing as phi bar dot, and this pi phi bar is the same thing as phi dot. Okay, in bosonic language, all our operators are functions of, as far as bosonic variables go, all our operators are functions of phi bar, pi phi bar. Okay, all good. The fermionic operators are generated by, let's call them sigma 1 plus minus. I mean, the fermionic Hilbert space is a 4-dimensional Hilbert space, and the operators that are useful in this Hilbert space, the operators that generate the Hilbert space, is sigma 1 plus minus and sigma 2 plus minus, where the dictionary is, just at least for now, is sigma 1 is equal to sigma 1 minus is equal to psi 1, sigma 1 plus is equal to psi 1 bar, sigma 2 minus is equal to psi 2, and sigma 2 plus is equal to psi 2 bar. Okay? So this is a Hilbert space. It's a Hilbert space of 4 functions of phi and phi bar of 2 variables. Okay? And it's on that Hilbert space that we want to write down an operator expression that will generate these transformations. Okay? So I tried to do this before the lecture, and I'm going to write down what I got, and then we'll check that it works, or you guys will help correct me. Okay? I got the following expressions. Q1 is equal to square root 2 I sigma 2 plus W bar prime plus sigma 1 minus pi phi. Q2 is equal to square root 2. Okay? Now, you might think all we have to do is take 1 to 2, is to take 1 to 2. But that's not completely correct, because we also had to take f to minus f. F was code word for this W. Okay? So we get minus I sigma 2 plus W bar prime plus sigma 1 minus sigma, sorry, what am I saying? 1 and 2 minus pi phi. Right? And then there's also Q1 bar and Q2 bar. And this you can work, I mean, we will check, but the mnemonic is that these two should be Hermitian conjugates of each other. Okay, so it's minus I sigma 2 minus W prime plus sigma 1 plus pi phi bar, and Q2 bar is equal to square root 2. Now Hermitian conjugate of this. So I sigma 1 minus W prime plus sigma 2 plus pi phi bar. This is my claim, and I'm now going to try to check it. Okay, I'm going to check it in 2 or 3 different ways. Okay, please. What? How did I arrive at this? By staring at these transformations. You see, let's take an example. Let's take Q1 anti-commutator psi 2. Okay, has to give us square root 2f. So then that tells us that Q1 should have a psi 1 times square root 2f. Because psi 1, should have a psi 2 bar times square root 2f. Because psi 2 bar anti-commutator is 1. Okay, and so this is psi 2 bar, this is the square root 2, and f is I W bar prime. Is that correct? F is I W bar prime. Okay? Well, that's part of Q1, but if I wanted to get the other part of Q1, let me see. Q1 on phi gives I square root 2 psi 1. Now phi, the only thing that has a non-trivial commutator with phi is pi. Pi phi is 1. Okay, so now pi phi is minus I, but phi pi is I. We're putting the Q on the other side. Okay, I wanted to get an I wanted to get a square root 2, and I wanted to get a psi 2. So I get the square root 2, I get the psi 2. Oops. Yeah, psi 1, thank you. I get the square root 2, I get the psi 1, and the I comes because commutator of x, x with p is I. Okay, so this is what I'm basically back calculating. I see these, and I work out what will work. Okay? What is slightly non-trivial is that there's one expression that works for everything. But it's only slightly non-trivial. There will be more non-trivial checks as we go on.
That means if there is another field which commutes with everything, I can add it to Q1 and it won't change anything.
Okay, yes. If there is a field which commutes with everything.
Commutes with everything, then I can just add that to Q1 and it won't change anything.
Yeah. So,
Irreducible algebra, we should not have that.
right. I think Kanu has in mind, suppose we had a free theory attached to this. Okay. Then Kanu's point is that we could just add, but wait, yeah, sorry. Give me an example of an operator that commutes with everything. There's no such thing, right?
Yeah, like both commuting and anti-commuting.
Yeah, let's take the Hilbert space of a particle in one dimension. There is no operator that commutes with all operators. Unless you're writing a constant.
Yeah, but within the identity.
So your question is, what about adding a constant? What about adding a constant to this to Q? Okay, Q should be a fermionic operator. It should be, you remember we started this class by saying we were looking at grading of operators. The operator had to be odd. So there's no fermionic constant. Right? Now, the kind of thing you're talking about in some situations, let's say that we were trying to generate the operator, find the operator that generates time translations in a quantum mechanical theory, for instance. That operator will have a constant ambiguity. This is the statement that the Hamiltonian, you can add 0 to it and change almost nothing in quantum mechanics, right? Okay? So in some situations what you're saying is right, that you can add a constant. This is not that situation. Okay? It's not that situation because even the Hamiltonian in this situation is the square of a supersymmetry. And the supersymmetry is unambiguously defined. So the Hamiltonian also doesn't have this shift symmetry in this situation. Okay? I hope I've understood your question. Okay. Okay, great. So let's check, one of these guys. I don't know, just somebody pick one of these four and let's check one of these four for everything. Q1 bar. Let's check Q1 bar with everything. Okay. So I want phi, anti-commutator of phi with Q1 bar. It's a commutator of phi with Q1 bar. Okay, so now phi has a pi phi bar. So I will get a square root 2 sigma 1 plus.
Phi bar will not commute.
No. Pi phi bar anti-commutes with phi bar.
Yeah, but here you are using phi comma Q1.
I'm using phi, thank you. So that's it. So this is 0, and let's write down the other one as well, phi bar, Q1 bar. So that will give us square root 2 sigma 1 plus, and now we get just I, right? Okay? I'll just write them all down and then we'll check against that board. Okay? What about psi 1 anti-commutator Q1 bar? Okay, so psi 1 clicks only with sigma 1 plus. There is such a thing here. So we will get square root 2 pi phi bar. But pi phi bar now, because we want to compare there, I'll write it as phi dot. Okay. What about psi 2 Q1 bar? Now psi 2 Q1 bar only clicks with a sigma 2 plus, but there's no such thing, so that's 0. What about psi 1 bar q1 bar. That's clearly 0 because q1 bar had only sigma 1 plus, no sigma 1 minus. So we get 0 because psi 1 bar is sigma 1 plus. Okay, and what about psi 2 bar q1 bar? Okay, psi 2 bar q1 bar. Well, psi 2 bar q1 bar, psi 2 bar q1 bar is sigma 2 plus, it clicks with that minus, so minus I square root 2 w prime. Okay, that's everything, right? What? F is dependent. We'll check in a minute that the F things work out. So we checked that last class, right? That the F worked with its equations of motion. So we can forget about F. You see, the operator expression will have no F in it. It's just a function of phi. So just the consistency of the commutation relations of F with the commutation relations of what you replace F with. We checked that last time. Okay, if you want, I'll check it again, but fine. Okay, so now just let's take this and compare with the left-hand side. So if I want q1 bar, okay, that I already have here. So q1 bar on phi is equal to 0, so that's check. Q1 bar, now I want q1 bar on phi bar. Here I have to use that rule. q1 bar on phi bar, we just make everything a bar. So I get I square root 2 psi 1 bar. So I should have written this as psi 1 bar when I'm writing in this language. So that's a check. Okay. Psi 1 q1 bar, psi 1 q1 bar square root 2 phi dot. So that's a check. Okay. These two, I'm writing checks, but please tell me if I'm doing it wrong. Okay, and let's look at this last one. Psi 2 bar q2 bar. So we want, sorry, psi 2 bar q1 bar. Thank you. Right, here. So we want to take, yeah, maybe I should just replace this f with what it is. F here is I w bar prime phi. Yeah, and then bar of that, not working, minus. You're right, you're right. I'm only allowed to use this bar rule when there are f's. I'm sorry, you're right. You're right. Let's write this as, what was this? Was this just f? Square root 2f. The rule was, as Shuman points out, we got that rule from Superspace, right? We got that rule from Superspace. We just use it by replacing everything with a bar and then use its equation of motion. What f bar is. So you're right, we should have got square root 2 f bar, but f bar was minus I w prime. Okay? So it works. Okay? You can check any one you want. They'll all work. I'm pretty sure. I sort of at least roughly checked everything. Okay? So these are our supersymmetry transformations for this complex problem.
What is the reason for this odd rule for this transformations to make it bar that you can't bar the I?
What was the reason? Well, we checked the reason. Right? We checked it, right?
Yes, we checked it. Like I am saying that.
More fundamentally, I think.
No, I mean that is the only point where you have to make this rule weird. That you are barring and you are not barring the I.
Yeah.
Phi bar like that, right? Without changing the sign of I. I mean, is it possible that you
Yeah.
restore that rule for this?
It's a good question. You know, you might have been scared that that would not be consistent.
No, I thought that would be true for q bar also here. In this q bar, you made I2 minus I.
No, that is an operator.
Oh, that is an operator.
You know, that's an operator in Hilbert space. You know, everything we're doing with superspace with some rules of algebra. In the end, here we're getting operators in Hilbert space. in Hilbert space, Q bar has to be the conjugate of Q. Now, Schumann, you might have been scared that this rule would not work consistently with giving Q1 bar. That might have been your worry, right?
And
Then we've just checked that it's working. Yeah. Now, okay. Now, but you want some way of seeing that it had to work like this. It's a good question. I wonder whether it's from the fact that when you have commutators, you pick up an extra minus sign when you take bar. You know, when you have, so let's say you have Q commutator A. You take dagger of this. This gives you A dagger commutator Q dagger. Now we want to represent the transformation as Q dagger commutator bar. So there's an extra minus sign somewhere that possibly is keeping track of that I. I would have to check it to be sure, but I think it sounds right. Okay? Excellent. Okay, one more check before we declare victory on this. Okay? The last check is that these guys should obey the supersymmetry algebra. Okay? So these guys should obey the supersymmetry algebra, so let's check that. Well, of course, Q1 squares to 0, that's sort of obvious. What about Q1 with Q2? Now, it's not completely obvious that Q1 and Q2 anti-commute to 0 because there's a sigma 2 plus and a sigma 2 minus. Those guys give you anti-commutator W bar prime pi phi. But there's also sigma 1 minus and sigma 1 plus. And those, sorry, so from the first thing you get I W bar prime pi phi. So suppose I calculate Q1 with Q2. I get I W bar prime pi phi from the first term. But you see, we also get minus I W bar prime pi phi from the second term. From, you know, the sigma 2s hitting each other give you the first term, and the sigma 1s hitting each other give you the second term. Is this clear? Of course, sigma 1 and sigma 2 don't talk to each other. And you might have been worried, what about the pi phi? Yeah. But remember, W bar is a function only of phi bar. Okay, W was holomorphic. W was a function of phi, W bar was a function only of phi bar. Okay? So the Q1 and Q2, the pi and the phi don't talk to each other because there's a function of phi bar and a pi of phi. Is this clear? Okay, great. Similarly, Q1 bar and Q2 bar will be 0. Just the complex conjugate of this. Okay, what about Q1 with Q2 bar? Let's break that down. What about Q1 with Q2 bar? Well, Q1 with Q2 bar, again, you might worry. You might worry because there's a pi phi bar and a W bar. But sigma 2 squares to 0. Sigma 2 plus squares to 0. So, you know, those two anti-commute with each other. What you get is, you would get a term which is sigma 2 plus, the whole thing square, times, you know, a W bar prime anti-commutator pi phi bar, or commutator pi phi bar. You get some term like this. But this is 0. So there was no point writing it down at all. Okay? So Q1 with Q2 bar is 0, and similarly Q1 bar with Q2 is 0. So that leaves only Q1 with Q1 bar and Q2 with Q2 bar. Okay? And let's work these guys out. So suppose I write Q1 with Q1 bar. What is that? Well, Q1 with Q1 bar, Q1 with Q1 bar, so let me get, Now we've got, you see, we've got many terms that could contribute. Let's look at the first term on both sides. That gives you, we get some contribution because of the anti-commutator of the sigma 2 plus and sigma 2 minus. I with minus I gives 1, that gives 1, so I get W bar prime, W prime. The anti-commutator is 1. Right? Psi bar anti-commutator is 1. Okay. So that's one term. Now let's take the next diagonal term, namely the second term of Q1 and the second term of Q1 bar. Okay. So that gives us, once again, the pi phi and pi phi bar commute with each other. So we get, oh, and I get a 2 because of the square root 2s. And then there's a plus 2 pi phi bar. Okay? And then there are the cross terms. So let's look at those. So what about the cross term which is that guy with that guy? Now the sigmas are on their own trip. Right? So let's write that out. Let's just write it out very explicitly. So we get square root 2, and now I'll take the first and the second. Okay, so square root 2i, square root 2i, sigma 2 plus sigma 1 plus 1 plus, and then W bar prime and pi phi bar. And then the second term is plus the other order, right? So the second term is plus, that's still the square root 2i, so I'll just take square root 2i outside. Now pi phi bar, and that came with the sigma 2 minus, sigma 1 plus, sigma 1 plus, sigma 2 plus, and W bar prime. Okay. Now we take these two sigmas and put them in the right order, I mean, whichever order we want. So square root 2i, let's call it sigma 2 plus, sigma 1 plus, so that's psi 2 bar, psi 1 bar. It's 2i, thank you. 2i, sigma 1 bar, and we'll get now the anti-commutator, the commutator W bar prime pi phi. Right? This minus this, because we switched order here. Okay? And then this is 2i, and this picks up an I. W bar, oh wait, pi phi bar, right? This gives us a W bar double prime times now just an I. Oh, I already wrote that. Thank you. I times W bar double prime. Okay. Times psi 2 bar psi 1 bar. Okay. And this is minus 2 W bar prime. So plus 2 W bar prime psi 1 bar psi 2 bar.
If we look in terms of sigmas, then shouldn't sigma 1 and sigma 2 commute rather than anti-commute? I mean, it's like a Hilbert Space tensor product of two spin half, right? Isn't it? And then sigma 1 will just act on first Hilbert Space and sigma 2 will act on second Hilbert Space.
Oh, I see. You're asking me why?
Shouldn't they commute rather than anti-commute?
This is a very good question, though. Right, right. It's a very good question. Maybe I messed up. Just hang. Okay. Okay. But you're absolutely right. No, but he's right, right? They should be designed to anti-commute. So I think what must be going on, just a minute. I think I've written my operator relations a little wrong, right? Because, in fact, my implementation of the algebra is wrong, because I said that size, Chintan's point. No, it won't help. Chintan's point was that I told you that psi 1 and psi 1 bar were sigma 1 minus and sigma 1 plus, whereas psi 2 and psi 2 bar were the others, right? This is what you're complaining about, and I think you're right. I think what we need is to put sigma 3 in the other. No, it's true. What he said is right, because we should get a minus sign when we interchange sides. So I've just implemented the algebra wrong. Excellent point, Chintan. Let's fix that. What I want is an element I want something that will anti-commute with both sigma 1 minus and I think that the right implementation, and thank you so much, is psi 2 bar is equal to sigma 1 minus, sigma 2 minus sigma 2 is equal to sigma 3 tensor sigma 2 minus sigma 3 tensor sigma 2 plus. Does this now work?
The previous one was sigma 1 minus times identity.
What? Yes, I was naively thinking of it as just being decoupled Hilbert spaces, decoupled operators, but Chintan correctly points out that that will not implement the fermionic rules. Okay? It's the same problem we have with gamma matrices. We want all the gamma matrices to anti-commute with each other. So we need to do this kind of thing. I think we need to do this kind of thing as here as well. Thank you very much. This would have led us at some point into trouble.
As long as you don't think of them as Pauli matrices, you don't run into a problem.
What?
As long as you don't think of them as Pauli matrices.
So what if you write them as side 1, side 2?
What?
In terms of size, if you write the Q's in terms of size.
But we want to implement it on a Hilbert space, right? We want the implementation in the, the point of this exercise is to go from the superfield formalism to the expressions in terms of a concrete Hilbert space. Okay? So we need the Pauli matrices for that, right? I think Chintan's points is excellent, and let's check that this is the right. Yeah, for gamma matrices like this. Go on, sorry, what? Psi 1 does not work in the other Hilbert space. Well, let's check. The only difference here is that psi 1, if I can find some operator here that, and then maybe I need, just give me 1 minute. Give me 1 minute. Yeah, no, it sounds good to me. So I want to find an operator here that anti-commutes with each of these. Now, sigma 1 plus and sigma 1 minus are linear combinations of sigma, the Pauli matrices sigma 1 and sigma 2. We know that sigma 1 and sigma 2 anti-commute with sigma 3. Therefore, sigma 1 plus and sigma 1 minus anti-commute with sigma 3. Okay? So previously, these operators just commuted because they were operators in just different Hilbert spaces. Now, every one operator anti-commutes with every two operator.
What if we take a sigma 3 of the other Hilbert space and multiply it with the sigma 1 minus?
I didn't understand. Hang on, let me just check that everything's working, then you raise your objections. Okay, so now what about the anti-commutations between themselves? This doesn't change anything, and this doesn't change anything because sigma 3 commutes with itself. Okay, so yeah, sigma 3 square, we just get 1. We just get identity. So this is actually implementing the algebra. Now, Kanu, what was your objection? Yes?
So, equivalently we can write psi 1 and sigma 1 minus tensor product with the sigma 3 from the other one.
I didn't understand you. Please say again.
In psi 2 we are taking the tensor product of sigma 3 from the first and sigma 2 minus from the second.
Yes.
Equivalently we can do the same for psi 1, sigma 1 minus.
We can do one or the other, but we shouldn't do both. We shouldn't do both because then it will overcompensate. Right? It's true, we've chosen one thing sort of randomly. Okay? But we shouldn't do both. Yeah. Okay? Okay. Excellent. 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 And now I need to upgrade my supersymmetry operators. So every time I have a 2, it should also include a sigma 3 in the 1. Okay, so what I'm going to do here is write a tilde with the understanding that sigma 2 tilde plus minus is equal to sigma 3 tensor sigma 2 plus minus. Thank you, thank you. You saved us for, at some point we would run into some inconsistency. Chintan, as usual, you guys save the class. So, thank you. Okay. Now, since the only thing we've ever used in getting all our algebra was the anti-commutators of sigma 1 plus, sigma 1 minus, sigma 2 plus, sigma 2 minus. Nothing in this algebra has changed. Okay, all the algebra we've done remains true here, and now what I was saying is true, right? Because we get this minus sign, so it makes it the commutator. Okay, so I hope everything else is okay. But yes, thank you very much. That was an important point. Okay, yeah, that's a bad mistake on my part. Right. So we get this. This. Are you all okay? Yes, come.
This phi side, they also live in the Hilbert space.
What, say again, phi and pi phi? Yes. So what is the Hilbert space? The Hilbert space is a Hilbert space on a four component, where these 4 components are alpha 1, alpha 2, alpha 3, alpha 4, and each of these is a function of phi and phi bar, square integrable function of phi and phi bar. Okay? The wave function is made up of 4 square integrable functions of phi and phi bar. And sure, phi and phi bar live in the Hilbert space. Phi acts by multiplying these wave functions with phi, and pi phi acts with minus I del by del phi.
They act on both the Hilbert spaces.
There's one Hilbert. What do you mean? There's only one Hilbert space. 1 and 2 were labels in superfield formalism. The quantization of that gives us a 4-component Hilbert space of 4 functions. Now there's only one Hilbert space. Please keep asking till you're satisfied. You can, eventually, the final Hilbert space is a 4-component space, which you can think of as a tensor product of two 2-component spaces. Yes, yes, yes. All the coefficients in this whole Hilbert space are functions of phi and phi bar. It's like when we do spin in quantum mechanics. There's a 2-component and there's x. What does it mean? The Hilbert space is 2 functions, each of x. It's like that. Okay? Okay, good. Excellent. So let us keep going.
Count the degrees of freedom. Should we say it's like 4 continuous real degrees of freedom, or should we? I mean, phi and phi bar are exactly not complex conjugates. So
Why aren't they complex conjugates?
aren't they independent?
They are independent, yeah. So what we should think of is that this is a particle with a 4-component spin moving in a 2-dimensional space.
2-dimensional, not 4.
Not 4-dimensional space. It's phi and phi bar. Phi plus, phi plus phi bar and phi minus phi bar, x and y.
But I am asking because phi and phi bar we are treating it like independent. No?
What do you mean by treating it like independent?
Phi 1 and phi 2 and then changing it to phi
Yeah,
2.
our Lagrangian was phi bar dot, phi bar dot phi dot, which is same as phi 1 dot phi dot, yeah, by 2, yeah, in the usual way. Right, it's just 2 dimensions. It's just convenience to group them in complex space. Okay, excellent. Other questions? Okay, so we computed this term, and then there is also the other term which will give us complex conjugate. And you recognize this as one of the terms that appears in the Hamiltonian. Okay, let's go back to maybe it's better this way. You remember our Lagrangian? Our Lagrangian was given here. So the Hamiltonian is pi phi bar plus mod w square, and then plus this term. Okay, this term I think has come with a plus, and I think it should come with a plus, because there are 2 different minus signs. When you go from the fermionic path integral to the fermionic Hamiltonian, you pick up a minus sign for the psi 1, 2, for the psi 2. And then when you go from the bosonic Hamiltonian, you pick up a second minus sign. So this, I think, we got it with a plus, right? We got it with the minus? Plus.
You will change psi 1.
Psi 2. Thank you. I don't want to give an explanation for an incorrect fact. But okay. Okay. What I'm saying is that if you look carefully at the transition between the path integral and the Hilbert and the Hamiltonian, because there is this fermionic business, you have to keep track of that, and that gives this extra minus sign. I think it all works and it's all great. Okay, so we're all very happy, right? We've got this. By the way, we also got the factor of 2. Every term came with a 2, and we wanted Q1 bar anti-commutator to be 2H. Okay, so everything's nice, and we're very happy. So we've checked this now in many different ways. I don't know if you remember, but we checked last time that the supersymmetry transformations square to 0 or square to the Hamiltonian when they should. Okay, since the transformations are those generated by these operators, that the operators will also have that property. So I won't separately check that. I won't. Okay, but in a way we have separately checked that because we've checked the algebra. So okay, we've really checked this thing wonderfully. Okay, so now using this thing, you guys are in good shape to complete the second part of the assignment, which is to find the supersymmetric ground states. That part I have not done, and I'm leaving that as an assignment. That's not a branch that leads to the next part of the lecture. Okay, so I very much encourage you to do that. I have the feeling that without Chintan's help, if you tried that exercise, you would have found no states. But Chintan's intervention has saved us that. I think we will find states. Okay. In fact, do you want to quickly check that? Give me 5 minutes. Let's take 5 minutes off to check. Let's work out the equations and leave it for you to solve it. Just to see, that'll be a last check, right? That we're getting consistent equations. Okay. Oh my. Okay. I will just write down the equations. I won't try to solve them because it really should be you guys doing the work. But I won't try to solve them. But let me at least see that we're getting consistent equations for this problem. Okay. Now where do we want to go? It's a pain that the camera won't capture that board. Okay, this should be enough. Okay, so let us suppose that our supersymmetric ground state was A up, 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 plus A up, down, up, down, plus A down, up, down, up, plus A down, 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 down. You understand what I mean, right? Up and down are in these two different, the tensor product space that's giving us our 4-component thing. Okay. Now, let's work out the equation that Q1 annihilates the state. Okay, that should be simple enough. So we won't worry about square root 2's because something annihilates square root 2 times that thing also annihilates it. So let's first look at the sigma 1 plus pi phi phi. So on this state, sigma 1 minus pi phi, sigma 1 minus only acts if the first guy was up. So only these two contribute. Okay, and we get pi phi, so we get minus I del phi, A up, up. And then it brings this guy down, right? Okay? And then what about this guy? It gives you minus I del phi, A up, down, and then brings this guy down. So this was psi, and Q1 psi 1 by square root 2. Q1 psi is equal to, so two terms we've written down. Q1 and psi. Okay, what about the other two terms? Now we have to keep our wits about us because of the sigma tilde. Okay, first thing, sigma 2 plus will only act if the second spin was down. Okay, so if the second spin was down, it could act here, and there sigma 1 3 will give you 1 because the first spin is up. Okay, so we will get this guy, so we will get plus A up, down, with an I, A up, down, and then W bar prime, and we will make this, that was plus, so it becomes up. Right? Now the next, it also acts on this guy. But there we will get it with a minus, because this was down. Okay, so we'll get minus A down, 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 and then up. W bar prime. Okay, wonderful. Now you see these terms come only this term, there's only one state proportional to up. W bar prime we assume is non-zero, so that tells us A up down is equal to 0. Since A up down is equal to 0, this is also 0, no further condition. Okay, eliminated. The interesting equation comes from here, because you get two terms with the same state. Okay, and so here we get minus I del phi. Let's take the minus sign out. So I del phi is equal del phi A up is equal to minus W bar prime A down. I left. Okay. This is equation number 1. Now I'm going to work it out with, I'm going to work out the equation that you annihilated also by Q2. I suspect that without Chintan's intervention, we would have got an inconsistent equation. Let's check that. That's what I want to check before we move on. Okay. So this was Q1 psi. Okay. Now let's look at Q2 psi. We should get the same equation, but I suspect that without Chintan, we would have got the two equations would not be the same. Let's check that we get the same equation, and just check what would have happened without Chintan's help. Okay, so let's take Q2 and psi and see what we get. 1 by square root 2 Q2. Okay, yeah. So now Q2 is just doing basically reverse things, but once again, let's first work out the W bar prime guy. Okay, so it's minus I, and then we want sigma 1 plus. So it only acts on the guys here that went down, last two terms, A down, up, and this makes it up. And because there is no tilde, there's no funny sign, and W bar prime. Okay, and plus A down, up, down, W bar prime. Okay, then we work out the other guy, which is the guy with the sigma 2 tilde, so we have to keep our wits about this. Okay, so sigma 2 tilde minus. So firstly, only the guys which are up on the second coefficient. So this guy can contribute. This guy contributes with minus I del phi. Minus I del phi. This guy is a plus, and this guy becomes, so A up, and then up, down. Right? And then finally we will get minus, now we will get here The other one that contributes is third term, because we have sigma 2 minus, but now we will get this with the minus sign. Minus, so plus I del phi, A down up, down up, down, thank you, down. Now once again we see that this guy and this guy being 0 tells us that A down up is 0. So that's fine. So just like there did we conclude A, we concluded here that A up down was 0. Here we conclude that A down up is 0. So both the off diagonal guys are 0. This guy and this guy are 0. And now this guy is the one that gives us same equation. You're seeing that faster than me. Yeah. What's this I here?
That's because of phi phi, right?
There's a minus phi I in the first term as well. So minus I is overall outside. Yeah, it works, right? Same positive sign relative. And therefore when you take it to the other side, minus. Okay, and just for complete satisfaction, let us check which signs would have changed without Chintan's help and see if we would have got an inconsistency. I very much suspect we would. Let's see. In this computation, here we would have changed our sign. So we would have had one sign flip here this was unimportant. That didn't matter at all. So here this calculation would not have changed. We would have got the same equation. But what about here? Here we would have had a plus sign here. So without Chintan's help, we would have concluded all four wave function terms were 0. Because we would have got A plus B is 0 and A minus B is equal to 0. We would have found A is 0, B is 0. And we would have been in big trouble. We would have found that there were no supersymmetric states, which is not true. Okay, so making mistakes like the kind I made would have had consequences. So now the assignment is now well-posed assignment because we've got well-posed equations. Of course, we can also work out the equations coming from Q bar 1 and Q bar 2. Of course, they will be consistent with each other, but they will be different from these equations. Right? They will be different from these equations. They'll effectively be sort of like the complex conjugate of these equations. And then you get two equations for two variables, both first order, and you have to solve them. That will be the problem of determining the ground states. Coupled equations. Yeah. So you will have some fun solving them. Just like a harmonic oscillator. Right. Sort of like a harmonic oscillator. It's a little more, yeah, sort of like a harmonic oscillator. I mean, are you thinking of the classical or quantum harmonic oscillator? Yeah, okay, that's a slightly easier problem because those would be ordinary differential equations in one time. Here we will have partial differential equations because we have Z and Z bar. So you'll have a little more fun solving these equations than the harmonic oscillator. But that I'm leaving to you.
What inner product will be, in the end you have to impose that the wave function is normalizable.
Yes.
So what inner product are we choosing here? Because
The usual inner product, L2 norm. So the inner product in this 4 cross 4 space is the one that makes sigma's Hermitian. You know, the up with up is 1, up with down is 0 in the line.
what about
Phi and fiber? L2 norm. So wave functions have to be square, are just integrated, you multiply and integrate over the space. The usual quantum mechanical norm. Right? So nothing unusual, nothing funny. Okay, all we are doing is looking at very simple quantum mechanical problems. These are problems you could have looked at in your first course on quantum mechanics. You know, at the point when you started studying spin, you could have studied all these problems. Right? So that's what's cool about this system. That we're encountering all the beautiful structures of supersymmetry in a system which has no mysteries. You know, you understand this totally. There's nothing you don't understand about the system. And yet you encounter many of the beautiful structures of supersymmetry in the system. Okay, so that's what's cool about it, and yeah. Right, so we're just doing quantum mechanics. The usual norm of quantum mechanics. Yeah. Okay, non-relativistic quantum mechanics, right? It's a relativistic theory of the world line, but in space-time it's non-relativistic quantum mechanics. It's just such a simple system, and yet see how much structure there is. Okay. Okay, let's move on. So we will declare that we have understood this system really well, and we will proceed to the analysis of the problem we started studying in the last class, namely the motion of a force supercharge system describing motion in many dimensions. Okay. Yeah. Now, in the last class, we started writing down the Lagrangian and so on, and we will come back to that at some point. But since we've gone through this whole exercise, what I really want to tell you about now, what I really want to discuss now is the supersymmetry transformations of that model. Okay? So, look here. What did we get when we took the simplest model? Suppose now, in the model that we were looking at in the last class was the many component analog of this, but with W equals 0. Oh, maybe we were writing it down in the last with the W. Let's suppose W is 0. So we're trying to do the analog of the sigma model that we studied with two supercharges. No potential. Later on turning on potentials. Okay? So if you've got W equals 0, these supercharges become pretty simple. They are sigma 1 pi, sigma 2 tilde pi, sigma 1 dagger pi, and so on. Okay? Notice that the first two have pi phi, and the next two have pi phi bar. Okay? Now you could ask, is this system implementing some natural geometry? That is, if we think of the phi coordinates, phi 1 and phi 1 bar, phi 2 bar, and so on, as coordinates on a 2n dimensional real manifold or an n dimensional complex manifold, is there some natural geometrical interpretation? Is there some nice geometrical interpretation of the Q operators? Okay? And in order to and the answer of course is yes. But in order to explain that to you, I'm going to give you a 10-minute primer about complex geometry. Okay? So we're taking a 10-minute break to review some mathematics, and then we will come back to this question.
Sorry, what was the question you wanted?
The question was this. Do you remember that in the two supercharge problem, the two supercharge analog of the sigma model, Q and Q bar had beautiful, Hilbert space was a set of forms, and Q and Q bar were the D and the D bar operators. Okay? So that quantum mechanical problem became a beautiful geometrical problem. Q and Q bar were very familiar. In fact, for people who do this kind of thing, it's one of the earliest cohomology problems, right? Cohomology of the D operator, the exterior derivative operator. Okay? Now, in our system now, we will have more structure, because we don't have just a Q and a Q bar. We have two Qs and two Q bars. Okay? So the question is there a geometrical implementation when we do the canonical quantization? do Q and Q bar become nice objects in geometry? Just like Q and Q bar in the two supercharged case became D and D bar, which were beautiful and very natural objects in geometry. Okay, so that's the question. Okay, so let's, before we take our diversion, let's start thinking like this. First, what is our Hilbert space? Okay, first, what is our Hilbert space? Well, clearly, our Hilbert space is made up of 2n fermionic harmonic oscillators at each point in space. Right? Do you remember the two supercharged case? If we had n coordinates, we had n fermionic harmonic oscillators at each point in space. Each oscillator could be occupied or not. And then we interpreted the occupation number as the degree of the form that we created. Right? And that matched with the fact that 2 to the power n, which was the total dimension of the fermionic Hilbert space, was same as the total number of coefficients in all forms, all antisymmetric tensors. Okay? So now we've got something very similar, because, because every coordinate comes with two fermionic harmonic oscillators, because there's psi1 bar and psi2 bar. But every coordinate also came with two bosonic directions, because there was phi and phi bar. So our Hilbert space now is 4 to the power n dimensional if we have n such phis. I hope you're understanding what I mean. You know, we're looking at a model where our phi and phi bar have indices I, and I run from 1 to n. So the Hilbert space is 4 to the n dimensional at each point in space, but the number of dimensions, number of real dimensions was 2n. So 4 to the power n is same as 2 to the power 2n. So once again the Hilbert space looks like it's going to be the space of all forms in this theory. Okay?
Going to phi bar was just a choice, right?
Going to phi bar was just a choice.
I'm just saying that you had made phi 2, phi 1, phi 2, and then you had made phi and phi bar.
Yes.
Now you are going to phi I,
If you want
phi
to.
I bar.
We
Like you could have done it with phi 1 and phi 2.
We could have done it. Yeah. The point is this. Actually, this is also an exercise we should do. But the point is that we could rewrite this Lagrangian in n equals 1 language as a theory with two n equal, that the Lagrangian that we get with n complex superfields, the final Lagrangian could be rewritten as a Lagrangian with 2n real superfields keeping only n equals 1 supersymmetry manifest. Once that statement is established, what you're saying makes this statement obvious. Okay? But we haven't established that statement. I'm trying to make that plausibility. Okay? So what I'm saying is that, in other words, what Schumann is telling us is that the model that we are studying, moving with n complex superfields, is a special case of an n equals 1 model, but moving with 2n real superfields.
But this chirality wouldn't be doing something.
Yes, it's a special case. I'm not saying that I'm not saying that every n equals 1 model with 2n superfields can be written this way. Certainly not. But I'm saying this can always be written in that language. This is natural, right? Because we've got a theory with 4 supersymmetries. But if we tried to write it in a way that made only 2 of these manifest, we would go back to what we did before. Okay? But not every theory we worked with before has 4 supersymmetries. So this is a special case of that. But it can be viewed in that language. This is clear? So once again, the Hilbert space of our theory is going to be the set of all forms. Okay? Now, what are these different operators going to look like? Well, suppose I take this guy and this guy and pair it together. Q1 and Q2 bar. Suppose I take this guy and pair it together. You see, can you remember why in the n equals 1 theory we got the D operator? We got the D operator because the supersymmetry operator was psi I bar pi. Yeah, psi I bar pi I. Okay, so we added one index and also added a derivative, which is what the D operator does. Okay. Now you see here what we are doing here. Okay, let's start here. What we're doing here is somewhat similar. Okay, because we're taking a derivative, and if you think of the total number of indices as the occupation number of this oscillator, this I2, we are also adding an index here because there's a plus. Okay, but you know, what we call plus and minus is entirely a matter of convention. Okay, what we call number of indices, it's entirely a matter of convention because it could flip to n minus number of indices if we just take the vacuum not to be the empty state but the completely filled state. Okay, so making that choice for the minuses, that is counting indices not from the bottom but from the top, this also becomes like an addition of an index. Okay, like an addition of an index times a derivative. Okay, what is the difference between these two derivatives? The difference is that while this is a derivative with respect to an anti-holomorphic index, this is a derivative with respect to a holomorphic index.
So you are saying one out of two spins, one spin ground state is empty and one spin.
We're going to choose that. We're going to choose the ground state, as he said, all the ones, let's say, to be filled and all the twos to be unfilled. Now, it's just a choice. It's just a matter of convention. What we call plus and minus, we could have called minus and plus. Who's to tell us, right? Right? Okay. So if we do that, then you see these two operators become very similar, except that one of the operators acts with a holomorphic derivative, and the other operator acts with an anti-holomorphic derivative. So this looks a little bit like the D operator, but acting only on holomorphic indices, or the D operator acting only on anti-holomorphic indices. Do you understand? Okay, and the mathematicians have talked about a version of this on Kähler manifolds. Okay, so that's what I want to briefly tell you about. This is what I want to briefly tell you about before we, yeah. Now.
So one adds a dz.
What?
Dz bar.
Exactly. So one of them adds a holomorphic index, the other one adds an anti-holomorphic index. And you add a holomorphic index by taking a holomorphic derivative, and add an anti-holomorphic index by taking an anti-holomorphic derivative. Okay? So the great thing about complex manifolds is that many of the things we can do in real manifolds split up separately for z and z bar. And that's what's going on here. So this is what I have to explain. Okay? I'm going to have to leave at 3:45 today. Let's do the maths at least. Yeah. Okay. References. The stuff that we've just discussed here, I did a basic web search. I couldn't find. I mean, of course, everyone knows it very well, but I couldn't find a canonical paper to this. So for this reason, I've just worked things out myself, mainly with your help. If somebody finds a reference which works this out, let us know. I'll circulate it to the class. I mean, I'm sure it exists. Mirror symmetry book. There you go. Kentaro Hori, that one. Yes. Great. They work out this model?
Yes, I think, but they use complex supercharger instead of they write like Q1 plus IQ2 as a Q and Q1 after that.
Wonderful. So the mirror symmetry book. So then we can also go and check there. Yeah. We can also go and check some of our algebra then. So thank you, Diksha. Okay. Okay, excellent. And for what I'm describing now, generally, just this basic mathematics, the book by Green, Schwartz, and Witten, Volume 2, the chapters on geometry, are a great place to look up everything, to look for more details, and then of course there are zillions of mathematics books. But okay. Okay. So I have to tell you what a complex manifold is. Okay. So let's start with a normal real manifold. These things we understand, right? These usual thing, you make it out of patches of coordinates which are analytic on overlaps, all that you know. Now, suppose we are given a quantity Jij, or let's call it Jmn. Okay? This quantity, in fact, we should call it Jmn like this. It's a tensor on this manifold. It has one index up, one index down. Now, because it has one index up and one index down, you can act on a vector. You can use it to act on a vector. Okay? And when you act on that vector, you will once again get a vector. Because the bottom index contracts with the vector index and leaves you with an uncontracted top index. So this Jmn can be thought as a map from tangent space to tangent space of the manifold. Vectors to vectors. Okay? Now, let us suppose that J square is equal to, okay, this is a general tensor, but now I'm going to focus on a particular kind of tensor. The kind of tensor which obeys the condition J squared is equal to -1. If you have such a tensor in your space,
What is J square?
J square is just J, multiplied by matrix multiplication.
Oh, okay.
Yeah, so it's Jm alpha, J alpha n. Okay? Suppose this quantity has the property that J squared is equal to -1. Okay, then as a matrix, all this quantity can only have eigenvalues plus I and minus I. Okay, if this guy is a real matrix, it will have as many plus i's as minus i's. Okay, so it's some such a tensor only exists in even dimensions. Okay, only exists in even dimension, and its eigenspace breaks up space into half of space, which is the plus I part, and the other half of space, which is the minus I part. Okay, anytime you have such a tensor in your manifold, a tensor like this on your manifold has a name. It's called an almost complex structure. Okay, so this thing is called an okay. Now, what turns an almost complex structure into a complex structure? You see, the point is that this J, first, before we start, what is the point of this J? The point of this J is to break up your tangent space into a part you're going to call holomorphic and a part you're going to call anti-holomorphic. So the plus I eigenspace is the holomorphic part, and the minus I eigenspace is the anti-holomorphic part. So it's J is something that, you know, takes x to y and y to minus x, in x plus iy being the complex direction, and or it takes z to iz and z bar to minus iz bar.
J when acts on a tangent space, it keeps the vectors in that space only?
Yes, because it's a tensor. It acts on a vector to give you a vector.
Yeah, but I thought it will give it vectors in a different tangent space.
No. It's a tensor on this manifold. So it acts, so it's a tensor field, right? This J is a function of where you are. Its indices lie up and down at one point. So it contracts at that point. So it keeps it at that point. Right? Fine. Okay. Now, the point here is that, fine, you can, if you want, use this J to define a notion of complex and anti-complex, or holomorphic and anti-holomorphic. But unless that notion has some differential property, some property that allows you to compare two things not just at a point, but move a little bit, okay, it's not a very useful notion. So somehow this complex structure has to mesh with the metric properties of your space for this to become a useful notion. Okay? And one way of saying this is as follows. Suppose we demand that Jmn, this quantity, is covariantly constant. Okay? This tells you then that the notion of a parallel of a complex, this tells you then that if you've got a holomorphic vector and you parallelly transport it, it will remain holomorphic. Right? Okay? So this is a good thing to impose. So if this is true that your J's, okay, that your J's are covariantly constant, then this complex structure, this almost complex structure is upgraded to a complex structure. Okay? Now one can work out algebraically what this covariant constancy of this J means. It's clearly some 3-index tensor, 2 down, 1 up, or 2 1 down, whatever. And there's a name for this. I can't quite remember. Neuvenhuis or something like that. Somebody, Diksha, what is this name? Okay, there's a name for this tensor. Just work out its components. And that vanishing is the condition that your manifold is what people call a complex manifold. Okay? And a complex scalar manifold. I mean, maybe there's some distinction between complex and scalar. I'm not distinguishing in what I'm saying here. Okay? Now, suppose you've got this okay. Now, suppose you've got this structure here. Okay, this J, by the way, because it squares to -1, is an antisymmetric thing. It's got mn indices, it's antisymmetric. Okay, and suppose I take the metric, which is Gmn in my space, and I act on it with a J. So I do J m prime m. Okay? Now because the metric is symmetric, but this guy is antisymmetric, this whole quantity is antisymmetric. So it's a 2-index antisymmetric object, which we sometimes call a form, right? It's a 2 form. Okay? Now, because this quantity here is 0, we know that the metric, all the covariant derivatives of the metric are 0. That's how you define your gamma, your Christoffel symbols. But all the covariant derivatives of this J are also 0. Okay? So that tells you that all the covariant derivatives of this this form. So we'll give this guy a name. We'll call it W. This is also 0. Now, in particular, if we take D of W, D was a 2 form. Sorry, W was a 2 form. If we take D of W, that is also 0. Because D can be written either with covariant derivatives or ordinary derivatives, makes no difference. But we write it in the representation with covariant derivatives, every covariant derivative is 0. So D of W is 0. Okay. So we get dW is equal to 0. W has a name, it's called the Kähler form. Okay, and we've just checked that it's a closed form. Yes? Why is dW 0? So what is dW? So dW is equal to, now you can write it with ordinary derivatives. We can also write it with covariant derivatives. I'll do that. Is equal to, so suppose dW, it's del A WBC plus symmetrized, anti-symmetrized, whatever, plus anti-symmetrized. That's what dW is. All the terms that make it anti-symmetric. Okay, but W was a product of J and G. All covariant derivatives of G vanish because that's how you determine the Christoffel symbol, to demand that's true. And all covariant derivatives of J vanish because we've demanded that. Okay, so D of the whole thing vanishes because each covariant derivative of this thing vanishes. Okay, now let's see. You see, this how are you saying that? J is antisymmetric because it squares to -1. Let's look. So J is because it squares to -1.
J is antisymmetric in this above and below.
It's antisymmetric. Actually, antisymmetric you can't really. It's only once you lower indices.
So you're saying WMN is antisymmetric?
I'm saying W is antisymmetric. I'm sorry. Yeah. Now, how am I saying that though? How am I saying that? Let's see. Let's see. It goes this way. Yeah, why is W defined this way antisymmetric? Well, let's check. Oh. Yeah, but yeah. I probably needed one more property. I'm sorry, I probably needed more property. Yes, you probably wanted that only G, Z, Z bar. That you probably wanted, sorry, I should have, yeah, you're right. You probably wanted that the only non-zero components of the metric are of the form G, Z, I, Z bar, J. Now this should do it. Now it does it, you see. Why is it antisymmetric? Because you see J acting on a Z index gives you an I, but J acting on a Z bar index gives you a minus I. Okay, therefore G was symmetric, but J times G was antisymmetric. Thank you, Chintan. Yes, so this was another condition we needed. We imposed the condition that the only properties, the only components of the metric that are non-zero are the Z bar components. Okay, thank you, yes. And then it's clear that it's antisymmetric, right? Because one side gives you an I, the other side gives you a minus I. Okay, but it doesn't change it otherwise. G was symmetric, but now we act with J. On one side you get an I, the other side you get no I. Okay, perfect. right? So had you looked at the other guy, j on that would have given you a minus I, but if I look at this guy, it gives you a plus I. Okay, so we see again, by the way,
Just like off diagonal in the z or
yeah, I'll just, exactly. All we have to do is to, so the only components that are non-zero are g, zi, z bar j. So I want to show that this is equal to minus g, z bar j, zi. Not g, k, w, omega. I want to show that this is true. First, sorry, let me be more systematic. Sorry about this. We soon have to stop, but sorry about this. Let me be more systematic. First, we demand this property. It then follows that W has the same property, that it has only Z, Z bar indices. Because J acting on a Z multiplies by I, and J acting on a Z bar multiplies by minus I. Okay? So you take something with the form G, Z, Z bar, and you multiply with J here, you get back something with Z, Z bar. Okay? But it'll never make it a Z, Z. Right, because it's just eigenspace. Is this clear? Okay, so that's good. Now, good. Now, we want to prove that this is true. Minus W Z Z, Z bar Z. We want to prove that this is the case. Okay, well, what was this? This was J, Z I, this was J M N, Z I, M, G, M, Z bar. But this J acting on Z, this only clicks when this is a Z. And J acting on Z gives you I. Okay, so this would be I, G, would be I, I, G, Z, Z bar. Z I, Z I bar. Z, J bar. Okay, but if we did it the other way around, it would have been the same argument except we would have got a minus I. Now G was symmetric, so G Z I Z J bar was same as G Z J bar Z I. Okay, but because of this I and minus I, this becomes anti-symmetric. Okay, thank you. This was important. Okay, so now we've got this nice form, and this exercise has also shown us that it's a kind of form that has one holomorphic index and one anti-holomorphic index. Any such form that has P holomorphic indices and Q anti-holomorphic indices has a name. It's called a PQ form. Okay, a PQ form is an antisymmetric object out of which only P indices are holomorphic and Q indices are anti-holomorphic. So PQ form is a particular case of an ordinary real differential form of degree P plus Q. Okay, so this W here, W was what we call a 1-1 form. I think we're going to have to go soon.
There is a lecture at
4 o'clock.
So we have to take 10 minutes to set up.
Give me 1 minute. I'll leave. Yes. Okay. Yeah. So this thing here is a 1-1 form. It has a name. It's called the Kähler form. Okay. Now the last thing I wanted to say, and then we'll complete this when we can. The last thing I wanted to say is that this Kähler form obeys d omega is equal to 0. Okay. From this, one can argue that, okay, suppose you had a gauge field and it obeyed dA was equal to 0. It follows from this that locally at least the gauge field is d of a scalar field. Okay? The fact that d omega is equal to 0 and that omega was a 1-1 form, okay, basically can be used to show, and I will show you when we do this next time, is that omega is omega z bar is equal to del zi del z bar j of some scalar, and omega z bar j z I is equal to minus of this, of the same scalar. The scalar is sometimes called k, and it's called the Kähler potential. Okay? Now, because omega and the metric differ only by an I, this tells you that the metric also has the property that it's del zi times del z bar j of some scalar function. Now let's go back to our model. Do you remember that we got a sigma model, but with the role of the metric being played by del zi del z bar j, del phi I del phi bar j of the function who p, the kinetic term that we put in. So you see that our supersymmetric theory was automatically a theory on a Kähler manifold. I'm going, yes. Okay, let's stop and we'll continue. Now,